So in this section, we will go over the basic concepts of logic. To be specific, we will talk about propositional logic. All right. So when we talk about propositional logic, what is the first term that we come across? Proposition, the term proposition. Now, what is a proposition? A proposition is a statement, a declarative sentence, which can either have a true value or a false value, but never both or never none. All right. Let's say, for example, it is cloudy today. This is a statement. This is a proposition, because this is a declarative sentence which can either be true or false, but never both, right? It is cloudy today. If it is indeed cloudy today, it's true. If it is not cloudy today, it's false. So you see, it can either have a true value or a false value, but never both. That is, it cannot be both cloudy and not cloudy at the same time. All right? It cannot be both cloudy and not cloudy at the same time. That is, a statement or a sentence which can have either a true value or a false value, but never both. That is a statement which we call a proposition, a declarative sentence like that. Now, why do we need proposition? So in our little word here that we have in this session, in this world, we will leave all our common sense and past experiences behind, all right, outside of this session. In this session, we will build all of our conclusions based on propositional logic, using propositional logic. If we don't know the truth value of a certain propositional statement, we will not try to derive it based on common sense. No, not from past experience. No, we will not do that. We will strictly use propositional logic for that. Understand this very clearly. Very often students get confused here because they try to apply the common rules of the practical world, or they try to apply common sense that they've developed over the years from past experience. Don't do that. All right. Here we will establish an idea, get to a conclusion strictly by using the rules of propositional logic. When we have a proposition, the statement, the value of the statement, the truth value, we call it the truth value. The truth value of the statement, whether it's true or false, that will be given to us. Based on that, we'll make some logical explanation and get to a logical conclusion, not using any past experience or any common sense from the practical world. That is outside of this session. This world is separate from that. Now, a statement in propositional logic, for ease of derivations or ease of logical analysis, a statement is usually represented using a propositional variable. That variable can be any alphabet, all right? Usually the norm is we use an alphabet to represent a propositional variable to represent a proposition. It can be P, Q, R, S, A, B, C, D, whatever. It is cloudy today. That propositional statement can be represented by the propositional variable C or B or whatever you want. Okay. Let's look at an example. It is raining. This is an example of a proposition. Why? Because this can have a truth value of either true or false, never both. It is raining can either be true or false, but cannot be both. It cannot be raining and not raining at the same time, right? So there you go. It will have either a truth value of true or false, hence it's a proposition. It is raining is a proposition. We are using the propositional variable P here, the alphabet P here, to represent this statement. Similarly, the propositional variable Q represents the statement it is wet outside. This is another example of a proposition. Again, it is wet outside can either be true or false, cannot be both at the same time. If P is true, we say that it is raining. If P is false, we say that it is not raining. If Q is true, we say that it is wet outside. If it's false, then we say that it is not wet outside, or in other words, it is dry outside. All right. Given that Q stands for it is wet outside. Okay. Now, logical operators. For logical operators, we have the not operator, the or operator, the and operator. This symbol here, this first one here, this one is symbol here, this one represents the not logical operator. We will always use this symbol for the not logical operator in propositional logic. You see this symbol, that is the not logical operator, or the negation logical operator. What does the not logical operator do? It negates a statement, all right? So if you have a certain statement P in, let's say for our previous example, P stood for it is raining. P stood for the statement that it is raining. Then what is the negation of P? The negation of P is represented in this format using the not symbol, not P. Not P stands for the opposite of P, which is it is not raining. The negation of P, which is it is not raining. Okay. So if the value of P is true, what does that mean? It means that it is raining. Then what will happen for not P? P will have the opposite truth value, the negated truth value, which is false. If P is true, then not P will be false. Hence negation. Since P stands for it is raining, and if P is true, that is, if it is indeed raining, then not P stands for the statement it is not raining. If P is false, however, then not P will stand for true. Whatever truth value P holds, so this is the propositional statement, it is raining, right? We do not know whether this is true or false. It can either be true or false. We do not know whether it's true or whether it's false. It can be either one of them, not both, but it can be either true or false. We do not know that yet. If P is true, then not P is false. If P is false, then not P is true. That is how we perform the negation, or that is how we execute the not logical operation. Okay, and that is the symbol for it. Not symbol used to the left of the variable. Okay, now this symbol here, this V symbol here, stands for the OR operator. We will always use this symbol for the OR operation. And what do we do in case of OR operation? What does it stand for? In case of the OR operation, between any two statements or more, it is defined such that the OR operation to any number of variables will have the truth value of true as long as at least one of the variables have the truth value of true. Let's look at this truth table, for example. Here we have two propositional variables, right? P and Q. How many propositional variables do we have here, guys? Two. So P or Q, we read it as P or Q. P or Q, the OR operator applied to these two variables, will have the truth value of true as long as at least one of them is true. At least one of P or Q is true. P or Q, the output will be true. If both of them will be true, if both of them are true, then obviously the output is going to be true. But as long as at least one is true, the output will be true. That's why you have true for the first combination when P and Q are true. The second combination as well, it's true because P is true. Even though Q is false, P is true. And in case of OR, all we need is for at least one of them to be true. So even though Q is false, P is true. That's why the output is true. And for the third again, even though P is false, Q is true, so the output is true. Only the last one has a truth value of false in the output because neither one of them, neither one of P or Q are true. Both of them are false, so the output is false. Okay. So that is the truth table of the OR operator. This is something we call the truth table. All right. A truth table where for each of the variables, you write down all possible combinations of truth values. Here, for example, see, how many variables do we have here, guys, in this truth table?
Two.
Two. Exactly, two. Each one of them, let's take P for an example. P, how many values, how many possible values can P have? Two.
Two.
Either true or false. Nothing outside of this, nothing more, nothing less. P can either be true or false. So possible, two possible truth values of P. Two possible truth values for P. It can either be, excuse me, true or false. Nothing else, all right? Same goes for Q. Q can either be true or false. Nothing else, okay? So we have two propositional variables, and each of them can have any of two possible truth values, okay? So what do we do next? We make a combination of all possible truth values. So we can either have true true or true false or false true or false false. You will see that these are the only four possible combinations of truth values for these two variables. If you bring in another variable, you will get more combinations, but as long as you have only two variables, these four are the only possible combinations of truth values. Now, why do we have four possible combinations here? Why? This comes from a formula. What is that? Here, the number of propositional variables, like you've already said, is 2. We have P and Q, two propositional variables. That is something we know from this truth table. Fine, set that aside. Each of these propositional variables can either have any of two possible results or two possible truth values. P can either be true or false, Q can either be true or false. This is true for all propositional variables in propositional logic. If you bring in any propositional statement, any proposition, like we've already discussed when we were defining a proposition, can either have the truth value of true or false. So possible values 2, any of the two possible values. So any propositional variable that you bring in, can have either one of two possible values. So there are two possible outcomes, always two possible values, all right? So this is going to be our base. 2 is going to be the base. And then the number of possible combinations of truth values in the truth table will come from the number of propositional variables. In this truth table, we have two propositional variables. That's why we have 2 to the power of the base to the power of 2, all right? 2 squared, all right? So 2 squared is 4, so 4 possible combinations. In the first truth table, for example, how many propositional variables did we have in the input? Just one propositional variable in the input. So 2 to the power of 1. 2 to the power of 1 is what?
2.
2.
2.
So there you go. 2 rows, 2 possible inputs, 2 possible combinations. Here we have 2 propositional variables, so 2 to the power of 2. So 4 combinations. What if we brought in another variable, let's say R? We wanted to construct a truth table that combined 3 propositional statements represented by 3 propositional variables respectively. In that case, we would not have just 4 rows. We would have
8.
in total 8 rows. 8 rows in terms of the combinations. I'm skipping the first row where we're just writing down the name of the variables or the output. I'm skipping the first one. How many, let me rephrase that and clear it out. How many possible combinations of truth values will we have when there are 3 propositional variables? 2 to the power of 3. The base is always 2. The base will always be 2 because in case of proposition, it can always only have any one of 2 possible values. So the base will always be 2 and 2 to the power of the number of propositional variables. In case of 3 propositional variables, like you've just pointed out, it's going to be 8 possible combinations because 2 to the power of 3 for 3 possible propositional variables, 2 to the power of 3 gives us 8. For 4 propositional variables, 2 to the power of 4 and so on, right? So now let's get back to the truth table of OR. So this is a truth table where we have all the possible combinations of truth values for the inputs, which are for the propositional variables PQ. These are all the possible combinations. And in the output, we have what we get once we apply the logical operation of OR. So P or Q will have these outputs. Now, let's move on to the next operator, AND, which is represented by this inverted V or a cap sign. This sign will be used throughout propositional logic to represent the logical operator AND. And what is an AND? We will define that based on the truth value of the output of the logical operator. If you compute the truth value of this operator, it will be true only and only when all the propositional variables in the input have the truth value of true. Look at this truth table, for example. The last truth table, the third one. How many propositional variables do we have here, guys, in the input?
2.
2.
Exactly. Exactly. So possible combinations of truth value is 2 to the power of 2, which is
4.
yes, exactly. And in the output, what do we have? You see, only the first combination has the truth value of true for the AND operator. Only the first one. Why? Because for the AND operator to give you, in order for the AND operator to give you a truth value of true, all propositional variables at the input must have a truth value of true. Must have a truth value of true. All of them. This will be true only and only when all of the input variables have a truth value of true, as you can see here. All of them, both of the two have a truth value of true. So that's why we have true in the output. In the second combination, for example, P has a truth value of true, but the output is still false. Why? Because
Q is false.
Q is false. And for AND, all of them have to be true in order for the output to be true. Same goes for the third one, and the last one, needless to say, both of them are false. Obviously, the output is going to be false, right? So there we go with the logical operators. And if you bring in more variables, it's going to be the same thing. If you had, let's say, what if we brought in three propositional variables here for the AND operation? For the AND operation, what if we had P, Q, R, 3 propositional variables? Then how many rows would we have? First of all, guys, how many possible combinations of truth values
8.
would we have?
8.
Why?
2 to the power
2
3.
to the power 3.
Exactly, 8 possible combinations. And the truth value of the output, which is P and Q and R, when would it be true?
Only when all the propositional values are
Only once.
So let's say P
When
and
all of
Q,
them.
let's say P has the truth value of true and Q has the truth value of true, just like this. Just like this first row, P has the truth value of true, Q has the truth value of true. The output is going to be true, right?
Yes, miss.
Yes.
Yes, the output is going to be true, yes?
The third
Yes.
one.
Depends on the R value.
Exactly, that depends on the R value. That was a trick question. Depends on the third variable. Remember, all of them have to be true. Even though P and Q are true, you don't know the truth value of R yet. I haven't said that. So from that, please understand, in case of AND, however many variables you bring in, all of the input variables must be true in order for the output of the AND operation to be true. Otherwise, if at least one of the input variables is false, the output will be false, right? Okay. Same goes for multiple variables for P or Q, or if you bring in a third variable, for example, if you have P or Q or R, in that case, you follow the definition of R for them as well. At least one of them, if it's true, then the output will be true. All right. So in case of P or Q or R, what we will have is only the combination where all of P, Q, R, all of them are false, only then the output will be false. Other than that, the rest of the combinations will have a truth value of true in the output. All right. Because in case of OR, as long as at least one of the input variables is true, the output will be true in case of OR. All right. Okay. Any questions?
No, ma'am.
Okay.
No, miss.
Okay then. So we had our propositional variables P and Q. Remember, they stood for it is raining and it is wet outside for our example. They may stand for something else in some other example or whatever, but the example that we've been working with so far, P stands for it is raining and Q stands for it is wet outside. Okay, so P stands for the statement it is raining. What will be not P? Not P as in the negation of P. It is not raining. Q stands for it is wet outside. What will be not Q? How would you write the statement not Q? The proposition not Q, how would you write it? It is not
It
wet
is not wet outside.
All right, exactly. That's how we, remember, if we have a statement, that is how we apply the not operator. You say you have a statement, it is raining, represented by the variable P. If I ask you to write down the statement represented by not P, you'd have to write it is not raining. Also, for not Q, it is not wet outside, all right? Instead of it is not wet outside, you could also write it is dry outside, as long as it makes sense like that, okay? So for or and, same thing. We had the statements it is raining, and the other statement is wet outside. P or Q stands for it is raining or it is wet outside, okay? So simply what did we do? It's just as simple as that. This variable P, what is the value of this variable? I shouldn't use the term value, I'm sorry. What statement or what proposition does this variable stand for? The proposition is it is raining. Just put that here, it is raining. And what proposition does Q stand for? It is wet outside. Just put that here, it is wet outside. So P or Q, if I ask you to write it down, then it would be it is raining or it is wet outside. P and Q, it is raining and it is wet outside. Now,
Miss, I have a
Okay.
question.
Yeah.
Miss,
go ahead, go ahead,
I have a question.
go ahead.
Miss, about this P and not P, can we have three variables like P, Q, and not P together in truth table?
PQ in the truth table.
Yes, Miss. P, Q, and not P.
Why would you need that?
I was just asking.
In the truth table. In the truth table, we construct the truth table based on what we need for the output. What you're saying, we can actually have that. You will actually look at cases of that, but it depends on what you need for the output. For example, here, what is it that we need to compute? P or Q, right?
Yes, Miss.
P or Q, in order to compute the value of P or Q, do we need to know the value of not P?
No, Miss.
No. So we do not need to include that in the truth table. Remember, we are studying computer science, aspiring to be computer science engineers. Computer science engineers are lazy. They find the least amount of work that can be done. They find that path, all right? If there is excess amount of work that is not needed, we don't do that, all right? We're lazy, okay? So if you don't need that, don't do that here, okay? Not
Okay.
P. You don't need to do that for P or Q. No need for that. P
We are
and
actually
yeah.
we're actually working with not P here too, right? So because P is when it's true, it's P, but when it's false, it becomes not.
No.
Is
No,
it?
no. This
Okay.
here, these are all possible combinations, okay? These are possible values that P might have, okay? Since there are, see, the reason you have two trues and two false here, because we're looking at the combination of both variables together. So here, when P is true, and it's not like this stands for P and this stands for not P. It's not like that. You don't know the truth value of P, okay? Don't get that confused. Thank you for your question. Thank you for your observation. I want you to understand that these two things are different, all right? In this truth table, the first one, for example, look at the first one, all right? P can be either true or false. See, P can either have the truth value of true or false. If P is true, then not P is false. If P is false, then not P is true, all right? So here as well, in the second one as well, P can either be true or false. You don't know whether P is true or false. You don't know whether it is raining or whether it is not raining. You don't know that. It is not, you're not, if the question tells you about the truth value, then you know, fine. But until it is told to you, you don't know. You don't know the truth value of P. You don't know whether it is true or false, okay? So in the truth table, we go with all possible combinations because P can be either true or false. If you say that when P is true, it stands for P. When P is false, it stands for not P. No, that's not the case. These are simply the possible truth values of P. Because P can either be true or false. We don't know whether P is true or false. All right? P stands for the propositional statement, it is raining. All right? P stands for the proposition, it is raining. P represents the proposition it is raining. Now, the value of P is a different matter, okay? P's value is not it is raining. P represents the proposition it is not raining. It represents that, fine. But the value of P equals what? P equals the truth value. And the truth value can either be true or false. You don't know that, okay? If P is true, it means that it is raining. If P is false, it means that it is not raining. A proposition, understand that a proposition can either be true or false. You don't know whether it's going to be true or whether it's going to be false, right? We don't know that. Is that clear now? Here. If you
Yes,
have
yes, ma'am.
confusion, go ahead and ask, because it's very crucial that you understand these things now, right now. Okay. All right. There are certain scenarios when you look at advanced logic, you will see that often we will represent the true truth value in the normal form and the false truth value in the negated form, but that is used in terms of derivation when we want to derive certain expressions or whatever. But when we are trying to compute the truth value of a certain operation or a certain combination of operations, we assume by default that the truth values of the input variables will have all possible combinations, all right? Because we do not know the actual value, all right? So we will consider all of the combinations, okay? So the difference between P and not P, here not P is the output, okay? So you see P can either be true or false. Whenever you know the truth value of P, then you can compute not P. If P is true, not P is false. If P is false, not P is true, all right? However, when we are looking at the input, by default, you cannot assume that when P is true, it's P. When P is false, it's not P. No, you cannot do that, okay? We consider all possible values because we don't know the result of P. If anybody else is confused with this, please go ahead and talk about it now, because we are going to build on this. If you don't understand this now, it's going to just create more complications later on in the future. Any questions? Okay.
No.
All right then. So now, okay. So just to expand a little bit on that, for example, I was talking about proposition. We were defining proposition here, right? That a proposition is a declarative sentence or a statement that can either be true or false, never both. It is raining. It's a proposition. What if I change it to, is it raining? That is not a proposition anymore, all right? Is it raining will have an answer, obviously. If is it raining can either have the answer of yes or no, but it's not a declarative sentence anymore. It's not a statement anymore. So it's not a proposition. A question is not a proposition. It's not a statement. It's not a declarative sentence, all right? Another example, the sun rises in the east. Can anybody tell me, is this true or is this false?
No idea.
The sun rises in the east. You don't know whether
True.
it's true or false.
Yes, a proposition, right?
True.
Positional variable बोले तो
Okay, so that's why I was getting there. The sun rises in the east. Okay, so see how I am framing this sentence. The sun rises in the east. All right. So this is something. First of all, the framing of the sentence, and more importantly, this is something that's a universal truth. Okay, the sun rises in the east. Will it ever have a false value? No, it will always be true. As long as you're on earth, it will always be true, all right? The sun rises in the east, so it will always have the truth value of true. So is this a proposition? We cannot strictly say that it's a proposition, because
No, ma'am.
this sort of situation, this sort of statements are termed as tautologies. A tautology. A tautology is a statement which will always have the truth value of true. All right. let's talk about another statement. If you do not study discrete mathematics, you will get an A. This is a statement. All right. Is this going to be true? Never. It's always going to be false. All right. In order to get a good grade, you need to study. So if you do not study, you will get an A is a contradiction. The two parts of the statement contradict each other. So it will never be true. It will always be false. Okay. This is a contradiction. Okay. So understand the differences. In case of proposition, in case of a purely propositional statement, we do not know the truth value of the proposition. It can either be true or false. All right. So when we say P stands for it is raining, we say that P represents the statement it is raining. But what is the value of P? P value key. What is the value of P? That depends on the truth value of P, which we do not know. It can either be true or false. It can be either one of them. So when we construct a truth table, we have to take into account all possible values of P, all possible values of Q, and the combination, all possible combinations of the truth values of P and Q. All right. That's what we do. Any questions? Okay. Now, P or Q stands for it is raining or it is wet outside. If I ask you to write down the statement P or Q, you would write it like this. Just what does P stand for? It is raining. So put that here. What does Q stand for? It is wet outside. Put that here. It is raining or it is wet outside. P and Q, if I ask you to write down the statement, you would write it like that. Now, let's say it is not raining. All right. It is not raining. That is, if it's not raining, then what is the value of P? What do you think? If it is not raining, can anybody tell me what will be the truth value of P?
False.
False.
Okay. So in that case, since P is false, since you've already said that P is false, and why is P false? Because it is not raining. P stands for it is raining. If it is not raining is true, if we say that it is not raining is true, that is, if we say that not P is true, then P must be false. So P is false. Fine. Now, since P is false, P or Q is going to be false as well, right, guys?
Yes.
Yes. Yes.
Yes,
P
ma'am.
or Q is going to be false because P is false, right?
It's an OR operator,
No,
so Q is still true.
Yes.
Technically
True
true.
again. True.
So yeah, you need to pay attention, all right? You need to pay attention. If P is false, since this is the OR operator, we are talking about P or Q, right? As long as at least one is true, the output will be true. So even if P is false, you have to check the truth value of Q. You have to check that. You still don't know the truth value of Q. You don't know whether Q is true or false. So even though P is false, you next need to find out the truth value of Q. What is the truth value of Q? If we say that it is wet outside is true, if we say that Q is true, then even though P is false, P or Q becomes what, guys, if Q is true?
True.
True, exactly.
True.
Exactly. When will P or Q be false?
If
When
Both of them are false.
When
Both are
both P and Q, both of them are false. When both P, Q are false, only then P or Q will be false. So bear that in mind, all right? Now, let's say we go with the same assumption that it is not raining. If it is not raining, then what does that mean? It is not raining. It means that not P is true. If not P is true, then P is false. Now, what happens to P and Q if P is false, guys? Do we need to find out the truth value of Q?
No.
It's false.
No, it's false.
It's going to be false because for the AND operation, in order for the output to be true, all of the input variables must be true. If at least one is false, the output becomes false. So P and Q, if P is false, you don't even have to check Q. By default, the AND operation will give you the result of false, all right? However, if it is raining, then what happens? then P is true, right? If it is raining, then not P is false and P is true, right? If this is true, if it is raining, if it is in fact raining, if it is raining, if this is true, it means that P is true, P has the truth value of true, and not P has the truth value of false. In that case, this P is true, fine. And then P and Q, it will have the truth value of true as well.
No,
No?
Not necessarily.
because we don't know.
Actually
We need
look
to
at
find
truth
out
value.
who is
We
true.
have to check the truth value of Q.
Exactly. Very good. You're wise to my tricks now, finally. Yes. P and Q will have the truth value depending on what the value of Q is, even if P is true, because it's the AND operator. All of them have to be true. P is true, fine, but then you also have to check whether Q is true or not, because it's the AND operator. If Q is true, then the output will be true. If Q is false, then what will be the output, guys?
False.
False.
So, have to be true. There you go. Okay. So now we will look at implications. So first we have the unidirectional implication represented by this unidirectional arrow pointing from left to right. Whenever you see this symbol, whenever you see this symbol between two operators, this symbol stands for implies. It is read as implies, all right? So you see this symbol you see between these two variables here. So how do we read this? This is read as P implies Q. Or in other words, it is also read as if P, then Q. What does it mean? It means that if P is true, then Q is true. Q is also true. That is, if P is true, then Q must be true. Then Q has to be true. If P, then Q. Right? If P is true, then Q will be true. This is how it is read. An implication. P implies Q, or if P, then Q, or if P is true, then Q is true. We also have another kind of implication. This is a bidirectional implication. You see the arrow points in both directions. This stands for if and only if. We will look at that in a short while after we look at this unidirectional implication at first, then we will look at this bidirectional one, all right, later on. First, we will try to understand what is the essence of an implication. That is, what is the essence of this statement, P implies Q, this one. What does this mean in terms of the truth table? We will look at that now. So we'll go by our previous example again. P stands for it is raining, Q stands for it is wet outside. Now, let's say we have a new statement. If it is raining, then it is wet outside. Say that you have this proposition. If it is raining, then it is wet outside, represented by the propositional variable R. If it is raining, then it is wet outside. So if you remember, it is raining is represented by the propositional variable P. It is wet outside, it is represented by the propositional variable Q. So this is essentially if P, then Q. That is, if P is true, then Q is true, represented by the implication here, right here. P implies Q. This one here, P implies Q. Okay. So in other words, we can also say that R equals P implies Q. Okay. So if this is the statement, then the truth value of R, the truth value of this statement, this entire statement, the truth value of this entire statement will be the same as the truth value of P implies Q. Okay. Or in other words, if in the question, if you have something like this, say this statement is not given. You know what P stands for, you know what Q stands for, and you're told that R is equal to P implies Q. From here as well, you can say that, okay, R must stand for the statement, if it is raining, then it is wet outside, based on this implication. All right, that's how we do it. Now, let's go into the truth table. So the truth table, as you can see here, for this statement, the truth value of this statement can be derived from the truth values of P and Q. How so? First of all, in the input, we have, again, two variables, right? So 4 possible combinations of truth values. The first one, where both P and Q are true, the output is true. Why is that? Because this combination satisfies the condition. This is a conditional statement. Yes, this is a conditional. If then is a condition, right? So if P is true, then Q is true. That is the condition. The condition is that if P is true, then Q has to be true. This is our condition. As long as this condition is satisfied, the output will be true, because that is our condition. This is a conditional statement. Now, let's see in this combination whether the conditional is whether the condition is satisfied or not. The condition says that if P is true, then Q has to be true. In this specific combination, P is true and Q is true. The conditional tells us that if P is true, then Q has to be true, which is the case here, right? So the first combination does satisfy the rule. The first combination does satisfy the condition. Since it satisfies the condition, since the first combination agrees with the condition, that's why in the output of the implication, the output of P implies Q has the truth value of true. So R will have the truth value of true for the first combination. Okay. Now, the second combination, we have true for P and false for Q. Here, let's see if it satisfies the conditional or not. What is the condition? If P is Q, then Q has to be true. Here, P is Q, yes. In the second combination, P is true, right? So, let's look back at the condition. If P is true, then what should be the truth value of Q? Guys, based on the condition.
True.
If P is true, Q should be what? True. In the second combination, is Q true?
No, miss.
No, it is not. So is the second combination satisfying the condition? Yes or no?
No, miss.
No, they're not. No, it's not. So that's why for the second combination, if P is true then and Q is false, if you have this combination, then it does not satisfy the condition.
Yes.
And it doesn't satisfy the condition, the output of P implies Q will be false.
False.
Because the condition is not satisfied, as simple as that. And hence, R will have the truth value of false for this combination. So far, it's straightforward for the first two combinations. It gets tricky for the last two. The last two are the ones which get a bit tricky. In the last two combinations, you will see that the truth value of P implies Q is true for both of them. Why is that? Look back at the condition, guys. What is our job here? Our job here is to make sure that the condition is satisfied in order for the output to be true. If the condition is satisfied, the output will be true. If it's not satisfied, the output will be false. Fine, straightforward. What is the condition? If P is true, then Q must be true. Okay, that is our condition. Now, why is the output true here then for the third combination? Why is the output true here then? Anybody has any observation?
No, miss.
Yes,
I
I
should
do.
be false, right? Because
No, it is true because it says if P is true, then Q should be true. But it does not say that if Q is true, then P needs to be true. So it's unidirectional. So
Come again?
it's an unidirectional conditional statement. So
So-
it implies that if P is true, then Q has to be true.
Yeah,
But
and
it does not say that if Q is true and P should be true. It can be different as well.
yeah, that's one way of looking at it. What I would like you to think about is an easier way, a simpler way to look at it. The condition says, the first part of the condition says, if P is true, okay, if P is true, then Q has to be something. Does it say anything about what happens when Q is false?
no, miss.
No,
ma'am.
it does not. It does not. So, if there is a scenario that the condition does not cover, then what happens there? It's a don't care scenario. The condition didn't cover it. So, by default, the output is true. Because the condition says if P is true, then Q has to be true. It didn't say anything about what happens when P is false. It didn't say anything about what happens when P is false. So by default, there is no condition to be satisfied, right? Because when P is true, Q has to be true. But it doesn't say anything about what happens when P is false. If P is true, right? So, but in the last two cases, in the last two combinations, P is false. This is not at all covered by the condition. So there is no condition at all to be fulfilled. By default, the output becomes true. It does not even matter what the truth value of Q is. You don't even have to look at it. P implies Q. The one on the left-hand side. The one on the left-hand side. If that is false, what does it mean? In case of a unidirectional conditional statement, in case of that, if the left side is false, by default, there is no condition to be fulfilled at all. If P is true, right? It doesn't say anything about what happens when P is false. For example, let's say, again, I would like to remind you that we will leave our common sense and all the things that we know from past experience and everything outside of this session. We will strictly go by what we know in terms of propositional logic. We will strictly go by the rules of propositional logic, right? Let's say after all of this passes, the entire deal with COVID and everything, let's say we have a better day someday, which will happen inshallah someday. And then again, the day you have to sit for an exam, you come into the university, you come into the classroom, and you sit for your exam physically, and you write your answer to the exam physically. All of that is done. So at the start of the exam, let's say, I tell you, if you talk to each other, I will cancel your exam. Okay? So let's say one of you, using the rules of propositional logic that I taught you, using that against me, one of you, let's say, goes ahead and looks at the script beside him or her, all right? And then I tell you, you looked at your friend's script, you're not allowed to copy from somebody else's script, I will cancel your exam. What could you say to me to retort at that point technically? Forgetting the rules of the practical world or common sense, or forgetting the fact for once that I'm on the other side of the desk where I hold all the power. Forgetting all of that. If I told you that I will cancel your paper if you talk to each other, and let's say Fardin, for example, Fardin goes ahead and looks at Ishtiaq's paper, and I tell him that I will cancel your paper. What could Fardin tell me at that point?
He can say that you told him to not to talk to each other, but you didn't tell him to tell him that he can look at other
Exactly.
topics silently. It's another don't care situation.
This is what we will do in these sessions, all right? We will approach these things in this manner. Fardin can tell me right away that, okay, you gave me the condition that if I talk to someone, then you will cancel my paper. You didn't say anything about anything else. I did not violate the condition. I did not talk to anybody. So you cannot cancel the paper. You cannot cancel my paper because I did not talk to anybody else. So by default, I did not break the condition that you gave me. All right? That is what you can do using propositional statements. In propositional logic, this is what we know. This is what we do. Forget about common sense. Forget about past experience. In the practical world, of course, Fardin says that and gets his paper cancelled and some more. But in the world of propositional logic, we go with what we know. We go with the truth value of the propositional statements that we know about. All right? Anything that goes outside of the condition, not our concern. Here, it's a conditional statement. As long as you satisfy the condition, it will be true. But if there is something that is outside of the scope of the condition, for example, P being false, so there is no condition to be fulfilled at all because it's not covered in the condition at all. So by default, it's true. Okay? All right. So does everybody understand how an implication works?
I have a question. I have a confusion about the example. So like if you said if someone, like if Fardin looks at someone Ishtiaq's copy, you can say like the exam is cancelled. You said before that if they talk to each other, the exam is cancelled.
Yeah.
So by default, if the first statement is like the first statement is not given in the condition, like Fardin is looking at someone's paper, but that's not, you did not mention that condition. So by
Yeah,
default,
very good point.
do
Yes.
you not have the right to like cancel the paper? Because like it should be true by default, like the second statement.
Yes, yes, yes.
Yeah.
Yeah. Yes, exactly. That basically puts me in the position of power. Very good point there. So his point is that, so see, what was the condition? What was the conditional? The conditional statement was that if you talk to each other, then I canceled your paper. All right, that was the conditional statement. Now Fardin looks at somebody else's paper. All right, and now then if I cancel his paper, if I do cancel his paper, his point is that the fact that he looked at somebody else's paper, that is not covered in the condition. So the second part, me canceling his paper, can either be true or false. But ultimately, the result of the outcome will be true. That is, if I cancel his paper, the outcome is true. If I don't cancel his paper, still the outcome is true. All right? That is what he's saying. Very good point there. Yeah. If you go by the rules of propositional logic, yeah, you head there as well. So very good point. Yeah. That is something that you can say as well by the rules of propositional logic. The reason I was talking about that is just for you to understand the idea of a conditional statement. How in a conditional statement, all you have to do is look at the first part. In a conditional statement, all you have to do is look at the first part and see whether the first part is true or not. If the first part is true, then you have to make sure that the second part is true. If the first part is false, it doesn't matter whether the second part is true or false. All right. So very good point there. What you said is exactly correct. Yes.
Yeah, nice, Fardin. You got your papers cancelled in the fake world too.
Yeah, good point there. So thank you very much for putting me in the position of power in the world of propositional logic as well. And very good at pointing that out. That is exactly the case in case of a unidirectional condition. A bidirectional condition is a bit different than this. We will look at that in the next class. In fact, we will pick up from conditional statement in case any of you have any questions after you go over all of these lectures. All right. I will upload this slide. I will upload the lecture recording as well. I'll stop the recording at this point. Right. Okay, there.